Welcome back to the Milli Locator, an energy harvesting dog or pet tracking collar. We are Team 5, Milli and the Volts. As a refresher, we are all online students. Joel is from South Texas in the top left corner. Myself, I'm in the top right. Jennifer in Houston, Texas. We have Kayla in the bottom left corner. She's from Arizona. And in the bottom right, we have Jordan, who is in North Dakota. So to start from the beginning of this semester, we began by acquiring the LTC 3106 harvesting chip. This is an integrated circuit from Linear Technologies that collects energy harvested from solar panels and thermoelectric generators and converts this into power used, for our case, a GPS module. In the left picture, you can see we soldered this chip onto a breakout board. As online students who have mainly worked in virtual labs, for me particularly, this was an exciting step in the development process to get my hands on something real and make it work. The middle picture shows the breakout board on a breadboard used to test the chip with actual components we would put on the collar. And the right photo shows a PCB designed by team member Kayla. It's cleaned up and has all the components soldered onto it. While we have learned a lot through this initial testing, we have learned more about our approach. With a shortage of these LTC chips in the market currently, we have begun exploring other solution paths. Joel will tell us about our original approach now.
Thanks, Jennifer. Now we'll talk about the original harvesting system approach. For this approach, we wanted to use the LTC 3106 energy harvesting chip in conjunction with a battery backup, flexible solar panels, and TEGs, which are thermoelectric generators. To do this, we need to take the LTC 3106 energy harvesting chip and we have to solder it to a breakout board. This will allow us to put all the components together on a breadboard for further testing. The team has been able to set up the breadboards with all the individual components, and we've done some initial testing. Some of the testing has included individual testing of each component to figure out what the maximum voltage and current specs are. And then we've put the circuit together and tested it as a whole to see what our output voltage and current is. Initial tests show that the battery backup is able to handle the voltage and current necessary to drive the GPS systems. The solar panels have proven to use the necessary voltage, but we're still lacking a bit on the current. And further testing is being done on the TEGs. I will now talk about the GPS. So for our GPS options, we had several GPS options that were being tested, but most of them, we couldn't get the data that we needed from them wirelessly. So we finally come up with a solution, and this solution includes using a Node MCU ESP8266 board connected to a U-Blox Neo 6M GPS chip and an external antenna. These, combined with a Blink 2.0 iOS app, will help us get the data that we need wirelessly. So for this, we had to program the Node MCU board using our Arduino software, and we've been able to accomplish this. And the board is able to talk to the U-Blox GPS chip and gathers the necessary data needed, which is being transferred to the Blink app wirelessly, which gives us our latitudes, longitudes. It gives us how many antennas we're using, a location, and a picture of a map as to where the dog collar is at. So this option has proven to work well for us and we'll continue to test it. Next, Kyla will talk about our second approach. Kyla?
Thank you, Joel. So the team's second GPS option is the LoRaWAN device with GPS. LoRaWAN is an abbreviation for Long Range Wide Area Network, and it uses open source technology to transmit data over unlicensed frequency bands. This device provides long-range GPS communication, with the range being larger than that of Wi-Fi. So by using this option, the successful operation of the Milli Locator would not be dependent on a Wi-Fi signal. The LoRaWAN board is also a low power device, which is ideal for the Milli Locator's harvesting system. And moving on to our modified harvesting system approach. With the initial results from the LTC energy harvesting chip being less than ideal, the team agreed to develop a modified approach. This approach was meant to simplify overall system operations while also giving us more design control than what was allowed with the LTC chip. After reevaluating our end goals for the Milli Locator, we realized that there were 3 things that we needed out of our harvesting system at a minimum. The first is that the life of the main battery can be extended through energy harvesting. More specifically, this is solar energy harvesting, since our previous tests showed that we can get more useful energy out of solar panels than we could with TEGs. The next is overcharge and over-discharge protection for the battery. This is something that we did not have with the LTC chip, and something that we feel is necessary for the protection of the battery as well as the rest of the system. And lastly, we concluded that we would like to have a 3.3 volt output, since many of the GPS options we have seen have a common 3.3 volt input pin. So our harvesting system needs to deliver at least 3.3 volts. Keeping these goals in mind, we conducted research and we were able to identify a charger IC and a protection system that would best suit our needs. The entire system can be seen in the image here on the slide, with each subsystem separated into its own block. As you can see, we have a block for the charging circuit, the battery protection circuit, as well as an added power path feature. The first 2 subsystems allow us to meet our original goals for the modified approach by trickle charging a lithium-ion battery, while also preventing overcharging and over-discharging. And the power path allows us to supply power to the load directly from the solar panel, and this is in the event that solar energy is available and the voltage supplied by the solar panel is greater than that of the battery. Under any other circumstances, the load will receive power directly from the battery. The overall system shown has been configured onto a PCB in a PCB design software and has been ordered for further testing. However, the solar charging subsystem has been tested on its own, and the team was able to verify that we can in fact trickle charge a lithium-ion battery through solar energy harvesting while simultaneously supplying power to a load. So once the PCB is delivered, the team will be able to test the battery protection and power path features in order to verify the overall system operation. And next, I will pass things along to Jordan, who will give some final details.
Thank you, Kayla. As has been described by previous team members, since the final proposal was submitted at the end of last semester, additional components such as a printed circuit board have been added to our design. Moreover, the addition of the second harvesting approach described by Kayla has necessitated additional budget items. The original final budget from last semester showed a total budget for a single prototype of $100.45, which included a $15 soldering kit. The current budget on this slide shows the total cost of the prototype components. Tools and testing equipment and materials such as a soldering iron and a breadboard are not included in these totals, but they were costs incurred by team members last semester. The largest additional expense is the cost of the printed circuit board. Though not included in last semester's proposal, the team realized that a PCB was necessary for a quality prototype and the additional cost was warranted. The design led to a higher PCB cost with the second approach. On the itemized budget, it can be seen that the power management chip, which is a higher expense on the first approach, is the LTC31 energy harvesting chip, while the second approach utilizes a buck boost converter, which is cheaper. A lithium battery is being used in the second approach as opposed to AA batteries to better align with the battery protection and circuit overcurrent protection design, leading to a higher cost there on the battery cost in the second approach. The GPS options are the same with either approach. Now, as Joel described, the unit that is currently installed and functioning on a breadboard prototype is a GPS with Wi-Fi. This budget also considers the fact that the final prototype produced may not include all the design elements originally considered for a waterproof dog collar. With that being said, the plan for completion includes assembling the final prototype with an energy harvesting system connected to the GPS unit and battery. Testing will include iteratively measuring the flow of current from the harvesting system, showing that current is flowing from the energy harvesting system to the battery and/or GPS unit over a period of time while the GPS unit is functioning. This will show that the unit is extending battery life on a functioning pet tracking device. As has already occurred, GPS data will also be collected and documented. The team plans to have the prototype attached to a harness or collar for purposes of final testing with the pet to show the GPS tracking capabilities. The team is on track to create a pet tracking device that utilizes energy harvesting to power the device or extend battery life. With that, the team of Milli and the Volts thanks its mentor, Dr. Keith Holberg, for all of his invaluable assistance and direction. And the team is looking forward to successfully completing this project and having a good experience on demo day. Thank you.